Wave-particle duality. So we have learned that light behaves as a wave. And we talked a lot about this. This is the electromagnetic spectrum. Now from Einstein's photoelectric effect, we have learned that light behaves as a particle, which is basically a photon. So light has a dualistic nature, which it was extremely revolutionary. When we say it has a dualistic nature, we say that it exists as both a wave and as a particle. Now, while talking about light as a particle or as a wave, Albert Einstein wrote, "It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do." So that's the key. Together they do. So light, you have a wave, and you also have this photon. Photon is like a packet of energy. So you have like a particle with some energy associated with it. This was extremely crazy at the time. Louis de Broglie, he capitalized on this dualistic nature. So he applied, or he thought, that if light can behave in some respects as matter, so i.e. a photon, as a particle, then perhaps matter can behave in some respects as light. So what that is saying is that you and I, we're composed of matter, right? We're composed of mass and volume. So he was saying, well, if we're composed of matter, maybe we can behave in some respects as light. Okay? So de Broglie proposed that particles could have wave-like character. De Broglie predicted that the wavelength of a particle was inversely proportional to its momentum, which is m times v. So it's given by this equation. Problem. What would be the wavelength in meters of a small car with a mass of 1,150 kilograms traveling at a velocity of 55 miles per hour? Okay, so we're going to use de Broglie's wavelength. Okay, his equation is given on the previous slide, where the wavelength is equal to h, which is Planck's constant, divided by mass times volume. Now, de Broglie said that matter can be composed of waves. So in our example here, we have a car. I'm not even going to try to draw a car because my artistic skills are awful. So here we have a car. He was saying that this car is going to have some wave-like property to it. So there's some wave associated with it. We need to figure out what that wave is. So we're going to use this equation and figure it out. We're going to punch in our what we have. So we have Planck's constant, which is a constant. So 6.626 times 10 to the negative 34 joules per second divided by the mass, which would be 1,150 kilograms, times the velocity. And they also give us the velocity. Which one do you think I should use? 55 miles per hour or 24.6 meters per second? You can honestly use either one, but one is going to be way more convenient. Notice here we have seconds. So we need to eventually get our seconds to cancel off. So I should use the 24.6 meters per second. Okay, now what units will cancel off? Okay, well, first of all, nothing is going to cancel. not even our seconds, because just the way of the math. You have seconds on top, and so you have to have seconds on bottom. But when it's meters over seconds, you bring that seconds to the top. So really what we have is seconds squared, if you're following me there. Okay, what we need to do is we need to look at joules. Joules is given by this these units. So instead of putting in joule, I'm going to put in these units. Okay, so we no longer have joules. We now have kilograms times meters squared divided by seconds squared. Now we can actually start canceling off units. Well, we can cancel off kilograms. One's on top, one's on bottom. We said that seconds and this seconds, they combine to make seconds squared. Okay, so the blue second squared is on top, the green second squared is on bottom, so we can cancel those units off. And lastly, with our meters, we can cancel off one of the meters. So one of those meters cancel off, and so we're left with meter on top. So that was a little tricky, but I think hopefully you can get it. Otherwise, ask me questions on it. By taking 6.6, that number, dividing by the bottom, we should end up with 2.34 times 10 to the negative 38 meters. Now that is the wavelength of this car. Okay, so the length of an atom, and this is just so you can get some perspective. The length of an atom is equal to 200 picometers. Pico means what? Do you remember what that means? Pico is very, very small. So if I calculated this out, it would be 2 times 10 to the negative 12 meters. Super, super tiny. So in comparison between the wavelength of a car and the length of an atom is going to be ridiculously smaller than an atom. But the interesting thing with de Broglie is everything that has matter has some wavelength associated with it. So if you are walking down the hallway, you are exerting some wave pattern. So it's pretty interesting. Quantum mechanics. Let's review the Bohr model. Now the Bohr model was really good because it helped determine that electrons have specific energies. So let's draw the Bohr model. We have the nucleus right in the center, and we have these energy levels. So we have the first energy level, which is pretty low. Then we have the second energy level, n equals 2, and that's going to be higher. And then you have multiple orbitals, so you can go from 1, 2, 3, all the way up. Now, each of these energy levels has specific energies associated with it, which we had seen, and so we say that they're quantized. The problem with the Bohr model is that it fails for atoms with more than one electron. If you were looking at helium, lithium, anything more than one electron, this model does not work. What they did to help understand, or to see what an atom really looks like, we have this guy named Erwin Schrödinger. He was an Austrian physicist, insanely bright guy, but he looked at electrons' wavelength properties, because remember, electrons are matter. And because of de Broglie, he said that all matter will have some sort of wavelength properties associated with it. So Schrödinger capitalized on that and said, well, because electrons are matter, I'm going to now, instead of looking at them as particles, as in like watching them move around. I'm going to look at their wave-like properties. So he disregards electrons moving in a defined path. The Bohr model definitely had that. The electrons were moving in a defined path. They were going all around the nucleus in a sense, kind of in a circle here. The quantum mechanical model, you don't have that anymore. There's no defined path to electrons. In fact, it is impossible to know precisely where an electron is and what path it follows due to the Heisenberg uncertainty principle. We're going to talk about that next. But before I do, I want to make sure you understand maybe one of my pet peeves. When you are looking at anything when it comes to atoms, you're going to see something that looks like this, right? And you have your nucleus in the center and you have electrons. This is an extremely bad picture of an atom, but you see it all the time. So I should denote this is an atom. But why is this picture wrong? The reason why it's wrong is because electrons no longer orbit around the nucleus. There's no defined path that electrons travel either. Instead, what we see is kind of this cloud. So we have this, it's called a quantum mechanical, or it's called the quantum cloud model, or quantum mechanical model. Both of them are the same thing. So what that is saying is that you have the nucleus right in the center, so you see that really, really small dot. And then we have electrons, and electrons, the blacker it is, the more likely it's found there. So you have an electron found more than likely here, and then as you move further away, it's getting more lighter. So an electron could be found there, or it could be found here. Notice how it's more spread out. So we now have this quantum model. We're going to look at this quantum model more. Before we look at the quantum model more, let's look at the Heisenberg uncertainty principle. It says when you try to observe the wave nature of an electron, you cannot observe its particle nature and vice versa. As you know more about one, you know less about the other. This is the Heisenberg uncertainty principle, and X represents the uncertainty in the position of the electron. M times V is the uncertainty in the velocity, or I should say the change in V is the uncertainty in velocity. H is Planck's constant, and it's divided by 4 pi. So we can never know both the position and the velocity of an electron precisely. If we know the velocity of one of the electrons with a high degree of certainty, then the position of the electron must be uncertain. Now, using the Heisenberg uncertainty principle, we can apply that to the quantum cloud model. On the left side, we have the classical model. So this would be according to like Niels Bohr. Niels Bohr, he said that electrons travel in a path. An example of this would be you have a pitcher throwing a ball to the catcher. You can track the electron, or you can track the baseball the entire time. So with Niels Bohr, he said you can do the exact same with an electron. You can track the electron the entire time. So the electron here could be found anywhere along this path. But in reality, you have the quantum mechanical model. The reality is you have a probability of where it's going to be found. And the reason why you have a probability is due to the Heisenberg uncertainty principle. Because with an electron, you never know how fast it's going, or let me back up. If you know how fast it's going, you don't know where it is. If you know where it is, you don't know how fast it's going. Okay, so based off of that, you have this probability. So an electron here could be found here, could be found there, over here. You can't know the defined path that it's going to be at. So looking at this catcher now in this figure, most of the time you're going to have a range of values. So 70% of the time the electron will be found in this area. Now if we shrink it, 40% of the time the electrons will be found in this ring. If we shrink it in even more, 20% of the time the electrons will be found in this ring. So now the next part of these notes, we are going to be looking at this probability, looking at the quantum mechanical model. Schrödinger's equation. If you remember from the previous section, we talked about Schrödinger a little bit, and he said that I am no longer going to look at an electron and try to figure out the path that it takes. So that was Niels Bohr. Niels Bohr said that electrons will travel in a defined path. Schrödinger, on the other hand, he looked at the wave-like properties of electrons. And so, based off of the Heisenberg uncertainty principle, he kind of came up with this equation. So Schrödinger developed what is called a wave equation to explain the quantum mechanical model. The solutions to the wave equation are called wave functions, i.e. orbitals, and are represented by the Greek symbol psi. Taking the square of the wave function, so psi squared, gives the probability of finding an electron within a given volume of space around the nucleus. So remember, Schrödinger, he said that according to the Heisenberg uncertainty principle, we can't be completely certain about an electron's position. So we can't follow the electron to see where it moves. So Schrödinger, he looked at the probability, that's the key there, of finding an electron within a given volume of space. Okay, so how he did this was he had the wave equation. This is what he kind of came up with. So the wave equation, known as like Schrödinger's equation, so he solved that wave equation, and that would give the wave function, which is known as psi. So an orbital is the same thing as the wave function. If you take the psi, or your wave function, and you square it, that will give you the probability, again there's the word probability, of finding an electron in a region of space. Each wave function describes both the allowed energy state of an orbital and a 3D shape of where the electrons are most likely found. These are going to be known as quantum numbers. We are going to be looking at the quantum numbers that help explain where an electron can be found. Now the wave function or the same thing as orbital. The orbital is going to be based off of the function, which is Fn. So it's going to be based off of these three quantum numbers, n, l, and m sub l. Well, what do those mean? That's what we're going to do next.